me start by focusing on this thing right here. If this doesn't look familiar, then you need to go back to the first video in this playlist that derives all this with a huge amount of algebra, which, of course, I love algebra. Now let's look at this. This was a function of rho, and rho happened to be equal to 2r over na sub 0. So what I'm going to do is bring that back in and restate this equation as a function of 2r over na sub 0. So we don't want to lose all this information that's there. This one, I've put 2l plus 1, which of course is 2l plus 2, but there's a reason for that. This is a special factor here, plus 1 minus 2r over na sub 0. Hopefully this doesn't cause you any headaches, because it's just restating it in such a way. And to bring in the 2r na sub 0 to everything, let's look at this equation. R to the nl, function of r, equals some constant. We haven't talked about this constant before. E to the minus r over na sub 0, 2r na sub 0 to the L. These are the exponential and the power term, so that this deals with r near 0, this deals with r near infinity. And this is an L. It might not look like an L here, but this represents the Laguerre polynomial, which is this thing. And here's the two factors. From the coefficient of the first derivative, this comes from the coefficient of the function itself. And we're going to say that that's a function of 2r over na sub 0. So there's nothing new here other than the 2r over na sub 0 being substituted back in. Now this constant, this is new. This looks very complicated. I've got this square root of those factors. Now notice this is a little different maybe than what you were expecting. All of this coefficient satisfies the following. The magnitude of the function squared times r squared dr, integral from 0 to infinity, has to be equal to 1, because the total probabilities of all the possibilities have to equal 1. Should be satisfying to you right now. N minus L minus 1 is the number of radial nodes. The nodes is the place where the probability drops to 0. 2l plus 1 is the number of orientations of angular momentum within that particular orbital range. And finally, the most general form of this whole thing, which involves the radius and the angles involved, is this form, which we covered up here, and this form, which we've seen before, which is the angular momentum part of this whole picture. This is going to give us radial nodes. This is going to give us angular momentum information so that we can predict the shapes of those. Now I'm going to shift from low gear to overdrive in one step. From the last video in Orbital Angular Momentum playlist, we introduced a ladder operator. This ladder operator can be expressed as the following. Angular momentum component of x plus or minus I times the angular momentum component of y. I brought these out here also. We might need to take advantage of those particular relationships. I put some other things up here just as a reminder of the angular momentum as a cross product of the gradient, which is kind of like the first derivative thing or first partial derivative thing. And here are the different components. Our goal is to get to trigonometric forms so that we can look at shapes for these different items. And so here we go, converting everything to spherical coordinates, which we've done in past videos. Here's the gradient in spherical coordinates. The R operator, this is kind of an operator thing, so we're breaking it out into R operators, theta operator, and phi operator, rather than X, Y, Z. And here's the first partial with respect to R, plus 1 over R. This should look familiar. This 1 over R here for the theta and 1 over R sine theta for the phi. Theta operator, first partial with respect to theta, and the phi operator, first partial with respect to phi. The total angular momentum is equal to this quantity, which we have up here. And if we convert that to spherical coordinates, in other words, we're just taking this and plugging it in, it comes out to look like this. Now, there's a special set of identities that are really going to help here. The R operator cross the delta operator equals the phi operator. And in like manner, the R operator crossed with the phi operator equals negative theta operator. We go from this form to this form. Let's see if we can follow that. We took the R operator cross and distributed it over these quantities, and then using these identities, it results in this form. L sub z is just I h bar first partial with respect to phi. And that's because Lz is only affected by phi. Now Lx and Ly, that's a different story, but for Lz, it comes out to this form. So all we've got is the phi angle involved. Now I'm going to flip the page because what we really want to do is come up with this thing converted to spherical coordinates. So let's see what I've got on the next page. Okay, here's the ladder operator, and instead of L sub x plus or minus I L sub y, I get x plus or minus IY equal to e to the plus or minus I phi delta operator plus or minus I phi operator. The y becomes the phi type thing and the x becomes the delta type thing. So this all coordinates into this final form of h bar e plus or minus I phi plus or minus first partial with respect to theta plus I cotangent theta first partial with respect to phi. Before I go on, I want to stress this is what we're after. The L and the M. Now what does the M do here? The M determines how many different orbital orientations we have. For instance, for the p orbital there are 3, for the d orbital there are 5, and for the f orbital there are 7. And those all have different L values. So what we want to do is figure out what happens when we change those M values to define the different orbital wave functions. But first, we're going to aim at just finding YLL, which would be the top spot. And then we're going to use a ladder operator to achieve the other states. We get it into the top spot, then we use a ladder down operator to move into the different levels. And by the time we're done, we'll look at y to the 2, 2, y to the 2, 1, and y to the 2, 0. I want you to concentrate on this first. The L up ladder operator on y, L, L has to be 0 because you can't go past the top state. Over here we have some things in a little toolbox. Here's the ladder operators in spherical coordinates. Here's the LZ in spherical coordinates. And here's the LZ operator on the YLM, which equals H bar M YLM. Now that was proved earlier, so this is something we have done in the past, which set that up. The fact that these are both LZ is really going to help out. So let me start with using those two together. I'm going to set these two equal. First on the right hand side, that's the easy one, H bar M Y to the LM. Well, since M equals L, I'm just going to say H bar L Y, and that's going to be L to the L. If we say that this first derivative of that equals HL, then that suggests an exponential. So that suggests the following. Partial of y with respect to phi equals IL y function. Now the h bar fell out because I can factor that out of both sides of this thing. So what does that tell us? That tells us that I'm going to say that the y angular momentum function is, or spherical coordinate function, is going to be theta and phi, and there's some function of theta. Haven't figured out what the theta function is, but I know what the phi function is, and that's e to the IL phi. Okay, where do we go from here? Well, what's going to be necessary is to take the derivative of this thing with respect to theta and the derivative with respect to phi. That's going to be needed to fill in this stuff over here. So let's see what that's going to be. The partial with theta doesn't do anything with this because there's no change, so that just becomes a constant. So all we do is say f prime, first derivative of this function of theta, e to the IL phi. Now what's the partial with respect to phi? That one's pretty easy. The f function is a theta thing, so that just stays constant. And the IL here comes out front because it's the derivative of this exponent right here. So we're going to use those two over here. Let's see how that works out. The first derivative thing, partial first derivative, is f prime e to the IL phi, I cotangent, and then we need to do the phi part of it, and that's IL FE IL phi. So I just used those two things and plugged them in over there. Now simplifying, I can factor out an e to the IL phi out of both of these. So that comes out front, leaves me with f prime minus L cotangent theta times the f function. I can use the exponent rule to combine them into this form, L plus 1, and let's see, no change there. The first derivative of theta minus L cotangent theta f phi, in other words, I just take these two, and if they're the same, then that would be 0, and that's what has to happen because this thing won't go to 0, but this thing is forced to become 0. So let's proceed on here a little bit. The first derivative of f with respect to theta equals L cotangent theta phi. Because this is a differential equation, I can work it around this way to say that the df over f equals L cotangent theta differential of theta. Now what I'm going to do is integrate both sides of this equation. That's going to be the integral of 1 over f df equal to L can come out front from the integral because it's a constant, and the integral of cotangent theta d theta. 1 over f df is natural log of f. So I can just say natural log of f equals L cotangent theta d theta. Now let's see what the integral is of cotangent. L natural log of sine theta. So I didn't bother to put all this on the page, just going to have to take my word for it. So that means natural log of f equals L times the natural log of sine plus some constant. So let's put that in this form. Removing the natural log from each side leaves me with the function equals some constant times sine theta to the L power. What would happen as we go from L comma L to L comma L minus 1, L comma L minus 2? What changes about this function? And what can we say about the shape or the positioning of these orbital functions? Here's what we just came up with on the last screen. The L down operator, we know that using an L up operator you can't go anywhere because you're already at the top. You can use an L down operator to see what the next L minus 1 value is. So here's the function that we brought over, which we saw before on the other one, whether you remember it or not. So in general, this is the way we can put it. We've got the M's in there now instead of the L's. So let me do the down operator on this thing, which is sine to the L power, EIL phi. And before we do that, you notice we're going to have to do some partial derivatives here. So I've figured out the partial derivatives already. The first partial of sine to the theta to the L power is you bring that power down here and then you subtract 1 from it. That's just the calculus derivative rules. And then we have to take the derivative of sine theta, which is cosine theta. Plugging this all into the form up here, you get L sine L minus 1 cosine theta e to the IL phi, which is all of this stuff. Now over here, we're taking the derivative with respect to phi, so this one's pretty easy. That's just IL e to the IL phi, and if we plug it all into everything, that's IL sine L, L powers don't change, e to the IL phi. So those things all plug in up here. Now what can we factor out? Well, what's common there? Well, we've got an IL sine theta that looks common, but at least we see the EIL phi can come out of there. So let's pull that out first. Inside here, I've done a little bit of work. First of all, where did the cotangent go? Well, the cotangent is cosine over sine, so that cancels out one of the sine thetas here. So that becomes L minus 1, and the two i's combined create a minus sign over here, and that cosine theta is left over from the cotangent. So if I pull minus L sine theta L minus 1 out of all of these, then that's going to leave cosine plus cosine, or make it simpler, 2 cosine theta. Moving the factors around, bring the 2 out here in front of the h bar, and there's also a minus sign there. So there we've got the common factor L sine theta L minus 1, cosine theta, and e to the I L minus 1q. Now notice one thing. The power went down here, so that would be m equals L minus 1, and then it would become Im, which is, again, it reduced by 1, like we'd expect. If we apply this to a fixed case, 2 comma 2, then that would mean this would be sine to the L, which would be 2, theta, e to the 2 I phi. That would be the general function. If we go on to the next one, notice this cosine digs itself in here when m equals L minus 1, and then when m equals 0, then that's going to be sine to the 0, and that'll be just 1, so we're left with 3 cosine squared theta minus 1. Now this last part, all I want you to do is focus on the cosine squared theta and not where the 3 and the minus 1 came from. What can we learn from these three functions down here? Well, when it's all sine, which is when the L is maximum, everything is pretty much along the z-axis. So think of it as maybe something oriented around the z-axis. Then as the cosine factor works in, then it starts tilting. And then as we increase to cosine squared, or in like f orbitals, you'd have even a cosine cubed, then it's starting to get really close to the horizontal versus the vertical z. So that's telling us what's happening with those orbitals. And that's really where I'm going to stop on this. So this should be the end of the foundations for now, unless I feel like I've left out something and we need to add something more later. So next, I'm going to start a playlist, which is my goal to do quantum computing and nitrogenase molecules. And we'll be building on these foundations because that's what I'm building on. I'm doing this as I learn. So I hope to see you there on that playlist.